Let's talk about the periodic table of the elements. This table is so helpful in so many ways, and understanding it is very important to understanding chemistry. So first things first, a row in the periodic table is called a period. Why? Because it's the one that repeats as we increase an atomic number. Remember that atomic numbers, which I don't have shown here in this version, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. But they go in rows. It's not like we go 1, 2, 3, 4, 5 this way. So when we count the elements in order, we are going across the rows, and the rows repeat certain characteristics. So that's why we call it a periodic table, because things will repeat in a predictable pattern. The columns are called groups. Why? Because we group these elements together. So for example, fluorine, chlorine, bromine, iodine all share characteristics, like for example, they form diatomics where they like to go in twos. So things in the same column like to do the same stuff. The reason why that has to do with electron configuration. And I have a video on electron configuration, but essentially how it works is each period or each row of this table represents adding on another shell of electrons. So as you go up in the number of shells, your electrons get farther and farther from the nucleus. And inside the shells, the electrons are organized in subshells. So we talked in the quantum numbers video about S, P, D, and F. So there's S subshell, P subshell, D subshell, and F subshell. And within these, you have orbitals, and an orbital accommodates 2 electrons. And it all sounds like very scary terminology, but it basically comes down to where is the electron probable to be. And where the electron is probable to be impacts how it reacts with stuff. So all of these elements, except for hydrogen, hydrogen's a weirdo, actually, hydrogen also has this. They all have like an S subshell that is half full, and that is their valence or outer shell. So that's another important term here is valence. Electrons are the outer electrons. So as you go down in the periods, as you get to rows that are further down, what happens is you keep on adding new shells, and all the ones on the inside have to be full before you can fill the outside ones. That's called the Aufbau principle. And we talked about that as well in the quantum numbers video. And what that means is that if you are able to add on electrons or take away electrons enough, you can get a full shell. And that is what all the atoms want. They want a full shell and nothing more and nothing less. So, for example, all of these guys that have 1s1 or 2s1 or 3s1 as their valence electrons or outer shell electrons, they like to lose 1 electron. Why? Because that makes them have a full shell underneath. So that inner shell becomes the valence shell, and they basically have the same electrons, not the same protons, but the same electron configuration as these guys, which we call the noble gases. And they're noble because everybody wants to be like them and have a full valence shell. So that's one way to categorize things is S, P, D, and F, and this way also explains why things repeat themselves in the periodic table. It's because all of the elements in the same group have the same valence or outer shell electrons. And we can look at the table before I go on, I want to look at the table in this form, and this just shows you where the F is actually supposed to go. I like to compare it to Alaska and Hawaii on the US map in that like they have them in little boxes, but this is not actually where they belong. They belong somewhere different. That makes the map really inconvenient to draw because we have to draw it big. So we tend to do it like this. The good news is we don't see the F block a lot, so I'm going to start to ignore it as we go on in conversation because it doesn't matter. So we can categorize the periodic table generally into metals and nonmetals. Metals are on the left, nonmetals are on the right. Metals like to lose electrons. Why? Because they are closer to that end of things. For example, lithium, that's here, has 1 valence electron. The first 2 electrons that are represented here, they are in the core or in the inner shells. But lithium has 1 valence electron. If it loses 1 valence electron, it will have a full valence shell. Also, if it gains 7 electrons, so if we gain 1, 2, 3, 4, 5, 6, 7 electrons, then we get to also a full valence shell. What's easier, losing 1 or getting 7? Losing 1. So that's why the metals like to lose electrons, because they're closer to that end of the table, and nonmetals like to gain electrons because it's easier for, say, fluorine to gain 1 valence electron than to lose 7 valence electrons. So it's easier for fluorine to get to the configuration of neon than to get to the configuration of helium back here. And when we say the configuration or the electron configuration, we just mean that the electrons in these atoms would look the same, but not their protons. So for example, if fluorine gains 1 electron, its electrons will look exactly like the electrons in neon, but the nuclei are still different. So that's also represented here. You can see the charges of the different groups, but also I want to make a whole video on ionic compounds and charges and all of that. Today I want to focus more on the structure of the table. So here's a more detailed view of what we name all the things. So these are good names to memorize. For example, here we have the alkali metals, and this is the first column, all except for hydrogen. Hydrogen is a weirdo because in the first row there are only 2 elements. So hydrogen is both the first and it's the second to last. So it shares some characteristics with the alkali metals, like for example, it can lose 1 electron and be happy. And it shares some characteristics with the halogens because it can gain 1 electron and be happy. And also it's not a metal. So hydrogen is kind of the exception to metals are on the left, non-metals are on the right, because hydrogen is a gas in most pressures and temperatures we'd be working with. So we have alkaline metals, alkaline earth metals, and these names don't really mean anything to us as chemistry students in the beginning, so they're just kind of memorization things. Transition metals, these ones are called transition metals because they are literally the transition between the metals over here and the non-metals over there. So they're called transition metals. And then the F block are called the lanthanides because the first element here is lanthanum, and the actinides because the first element here is actinum. And again, we don't see those a lot, so we don't really care about them, but do know that they're called the lanthanides and the actinides by the row. So like the top row is lanthanides, bottom row is actinides. And then we have post-transition metals here. So my rule with metals and non-metals, when we don't have all these little categories of alkaline earth, like post-transition, etc., when we're just talking about metals and non-metals, I like to say that if it's on this side, it's a metal. If it's on this side in the P block, it's a non-metal, unless it has a metal sounding name. So for example, in the P block, there is like tin and lead. So those are obviously metals, and they are metals, even though they're in the P block. But in this more detailed view, we have post-transition metals, so all of these guys are metals. And then we have metalloids, which is like this staircase here. And the metalloids are good at being semiconductors because you know how metals conduct electricity and non-metals like styrofoam, I know that's a compound, not an element, but if you think about that, that's an insulator. So metalloids that are kind of in between, they kind of conduct and they kind of don't, and that's what they're known for. And then we have just other non-metals, and then the halogens are here, and the halogens tend to be gases. They also tend to be diatomic. Iodine's a liquid, that's an exception, but they tend to be diatomic, so like F2, Br2, they tend to go in pairs. And then also we have noble gases. Everybody wants to be a noble gas because they have a full shell of valence or outer electrons, and they don't have any extras and they don't have any deficiencies. Usually we're going to be working in like this part of the periodic table. The elements down here in gray, they're so new and they're only made in a lab, so they're so new that like we don't know anything about them, or not anything, but we don't know enough about them to really characterize them in a category very well. And they've all got like really crazy sounding names. So it's this whole part right here that we usually don't work with. And another reason why that is because all of the elements that tend to be involved with living organisms have to do with up here. I know it's weird to see transition metals in living organisms, but we do have them in trace amounts, and some are very important, like iron helps us transport our oxygen. But my point in that is that a lot of people that have to learn chemistry are people that go into things like biology or healthcare, and then we see a lot of the top of the table. But this is the detailed way to categorize it. And then we had like metals and non-metals. We had charge forming and we had S, P, D, and F categorization. So now that I've gone over all of that, I want to go over trends. So for periodic trends, we have a few of them that are important, and I want to start with atomic radius. So atomic radius is how big you are, because if we think of the atom as a sphere, then if you have a bigger radius, you have a bigger sphere, because you have like a bigger number to cube, right? So if we're looking at atomic radius, what factors influence this? Well, remember that the atom is mostly empty space. So it all comes down to how many electrons do you have out there, and also how tightly are they held by the nucleus, because remember, the nucleus has protons, and the electrons and protons have opposite charges that attract. So as we go across the period, what happens? Well, we're not getting any more electron shells. We are getting more electrons, but we're not getting more electron shells. So even though we're adding on like 1 or 2 or 3 electrons, or 7 or 8, it's not really important because they're all kind of in the same distance from the nucleus. So that doesn't matter. What does matter is that we're getting more protons, because this means that the electrons are attracted closer to the nucleus. So as you go across the row, your atoms are going to get smaller. So for example, if we were to compare lithium to fluorine, which one would be bigger? It would be lithium, because as you go across the row, things get smaller. They have the same number of electron shells. They're both in the second row, so they're in the second electron shell. But lithium has 3 protons, and fluorine has 9 protons. As we go down the column, or down the group, what happens? Well, we're gaining more protons, but the more important thing is that we're gaining more electron shells. So now it matters, because when we make a new shell, we put everything farther away from the nucleus. That's why they're in a higher shell or a higher energy level. So as you go down, you're getting more electron shells, so your atom is going to get bigger. The atomic radius gets bigger. And this is also due to something called shielding, which is going to become important. So if I have a nucleus that is positive, and I have an electron that is negative, and it's here, then these two experience attraction. But if that one's on the outside and I have a lot of electrons on the inside, then this electron experiences repulsion here. So opposites attract, like charges repel. So if you have more electrons on the inside, then the valence electrons, which are the outermost ones, so they determine the radius, they're going to experience not only attraction toward the nucleus, but repulsion away from it. So that's going on. So the general trend for this is that down here we have big atoms, and up here we have small atoms. Usually when they ask you these questions, they will compare things that are easy to compare. So if the general trend is this way, then I'm not going to ask you to compare carbon and phosphorus, right? Because across the row, we would say that phosphorus is smaller, but down the column, we would say phosphorus is bigger, and that's complicated. So nobody's going to do that to you. They're going to compare carbon and nitrogen, or maybe nitrogen and silicon, where we can say, okay, both the factors for nitrogen and silicon are the same. So nitrogen has 2 things going for it to be small, both the protons being up compared to the row, and the electron shells being down. So that's atomic radius. The next trend I want to go over is electronegativity. So what is electronegativity? Electronegativity is how badly do you want to hold on to electrons? And that becomes really important as we talk about polarity later on in chemistry. So electronegativity is how badly do you want electrons, and it's based on some of the same things that go on with atomic radius. So what happens as we go down the group? Well, down the group or down the column, what happens is shielding. So like we talked about, if I have one atom that looks like this, and one atom that looks like this, so it's got like more shells of electrons, and I know these are really bad drawings, but hopefully they get the point across. And then for both of them, we have a hypothetical electron out here, and it's like, how badly do we want to hold on to that? Well, we're going to be experiencing attraction toward the nucleus from the protons and repulsion away from the nucleus by the other electrons. But here we have number 1, with more shells, this attraction is farther away, so it's weaker. And number 2, with more electron shells, we have more repulsion because we have more electrons that are repelling us. So as we go down the group, we get more electron shells, we get more shielding, we get more repulsion, we get lower electronegativity because we don't want the electron as badly. We have enough of them. We don't need another one. So electronegativity down the group gets worse or gets lower. What happens as we go across the row? Well, across the row, we do not have any more electron shells, so we don't have any more shielding. The electrons that we gain as we go across the row for periodic trends, they don't matter. They're negligible. It's going to be about how many electron shells or how many electron energy levels that you have. So remember that the shell or the energy level is the 1, 2, 3. It's not the SPD. So as we go across the row, no new electron shells, but we do get new protons. And the protons, what do they do to an outside electron? They attract it. Protons and electrons are opposites, so they attract. So as you go across the row, then you get more electronegative because you want electrons more badly. So the trend is that electronegativity is low here and it's high here. So fluorine is actually the most electronegative element. There are exceptions to these electronegativity trends, to the general trend going this direction, but you're not going to be asked about those exceptions probably. So low on the bottom left, high on the top right. Think about fluorine, the most electronegative element, and then you will remember how the trend goes. So we covered atomic radius, we covered electronegativity. The next one that I want to go over is called ionization energy. And ionization energy is kind of almost the opposite of electronegativity, because in electronegativity, we were asking how badly do we want electrons? And ionization energy is how okay are we with losing an electron? So ionization, an ion is a charged atom, so it's either lost or gained an electron. In ionization energy, we're always losing electrons, we're never gaining. It's always a hypothetical situation of if I was going to lose one electron, how much energy would it take? So let's compare down the group again, and surprise, surprise, this has to do with shielding. So if it has to do with shielding, I'm going to draw 2 of them that have different amounts of electron shells. So the one on the right has more electron shells, the one on the left has less. I don't know why I keep erasing them, but what's going to happen is we are going to ask, how difficult would it be to yank this guy out of the atom or yank that guy out of the atom? Which one do you think would be easier? Which one do you think would be more difficult? Well, with shielding, the one on the right is actually going to have more repulsion by the electrons that are inside, the core electrons. It's also going to have less attraction from the nucleus because the nucleus is farther away. And when you make things farther away, they don't attract as much. And I hope that's kind of a bit of common sense. And it doesn't take a lot to memorize. But with this, which one do you think would take more energy? This one would take more energy because you have more attraction and less repulsion. So the electron wants to stay. The electron on the other atom does not want to stay as badly because it's being repelled by more electrons and it's farther away from the nucleus, so less attraction. So the ionization energy is high here and it's low here. So as you go as you go down the group, ionization energy is going to go down. As you go up the group, ionization energy goes up. And then what happens as you go across the period? Remember that electrons that we gain across the period or across the row are negligible because we're not gaining any new electron shells. We're not adding important or significant shielding. So as we go across, the only thing that matters is we are gaining protons. If we gain protons, their job is to attract electrons. So it's going to be a lot harder to let an electron go if you have more protons. So if I'm going to compare, for example, silicon versus chlorine, then it's going to be a lot harder for chlorine to take away an electron than silicon because it has more protons. Another way to think of it is that remember that metals, or elements on this side, like to form positive ions. They like to lose electrons because it's easier to lose 1 or 2 than gain 6 or 7. And then nonmetals on this side, they like to gain electrons, except for the noble gases. They don't like to gain, but they like to stay how they are because it's easier to gain for most of the nonmetals than to lose. So in ionization energy, if I'm comparing, let's not compare silicon, let's compare sodium. If I ask sodium, would you like to take away 1 electron? Sodium is going to say, yes, definitely, that is my dream in life. Then I will become like the electron configuration of neon, and I will live happily ever after. If I ask silicon, which is in the middle, silicon will be like, okay, sure. Chlorine, on the other hand, if you try to take away an electron from chlorine, chlorine will go, are you serious? I was 1 electron away from perfection, and now you want to take 1 away so that I'm 2 electrons away? You're going to make life harder for me? No freaking way. And if you ask argon, which is over here, argon is a noble gas. Argon is going to say, get out of my noble castle and leave me alone because I am perfect exactly the way I am. Do not mess with my perfection. So ionization energy does include the noble gases. Some of the trends do not as much, like you won't be asked as much about them. Like in electronegativity, I've never seen a noble gas get put on an electronegativity question. For ionization energy, they will ask you. And these guys have high ionization energy because they don't want to lose an electron. It's going to be really difficult. It's going to take a lot of energy. So this is actually what I've been explaining is called first ionization energy. So we have first ionization energy and we have second ionization energy. So remember how we asked sodium, would you like to take away an electron? And sodium said, yes, definitely, that is my dream in life. Okay, well, let's say that we did. And now sodium has the electron configuration of neon. So it's got 1 more proton, it's got 11 protons, it identifies as sodium. But its electrons look exactly like neon. Sodium is basically now a noble gas. It's not going to be a gas, but it's going to be as happy as a noble gas. And that means when we go to second ionization energy, which is how much energy does it take to take away a second electron? Sodium, which is now sodium plus because it lost the negative electron, is going to be like, no way, get out of my noble gas castle. I'm living my perfect happily ever after dream. Leave me alone, don't take away my electron. So even though the first ionization energy for sodium would be low, the second ionization energy would be high. It turns out that the second ionization energy of any given element is always going to be higher than the first. What about if I had magnesium? If I took away an electron from magnesium, magnesium's like, okay, sure, that gets me closer to my goal of losing 2 electrons because 1, 2, we can count the columns. But if we take away a second electron, magnesium's like, oh man, I can't believe my luck. Now I look like a noble gas. So intuitively, I used to think that if you have a second ionization energy for the second column, it would be lower. It would be easier to take it away because now you look like a noble gas. But it turns out that if you're taking away an electron from magnesium that had an electron taken away, if you have taken away 1 electron, it's magnesium plus because it is positive. It's lost the negative electron. Now it's got more protons, more positive charge than electrons, negative charge. So we took away 1 electron, and now we want to take away another one. We want to take away something negative from something positive and make it even more positive. So even though, usually magnesium is going to form 2+ ions, that ionization energy is technically higher. It's always going to be higher to make something that's charged even more charged. It's going to be higher energy. Even if it's something that we see really often happening to that atom or that compound. So that's the story with first and second ionization energy, and we can continue on with third and fourth and fifth, but nobody does. But we can compare either first and second of one element, or we can compare like the first of 2 elements that are different. there's also like, you can compare the first and the second of different ones. So like to compare the second ionization energy of magnesium with the second ionization energy of sodium. Now remember, when magnesium loses its second electron, it's like, I'm already positively charged, so I don't like this, but also I do like it because then I'm going to look like a noble gas. Whereas sodium, when it loses a second electron, it's going to say, no, I'm a noble gas now, you can't take away a second electron from me, I don't like that. So the second ionization energy of sodium will be higher than the second ionization energy of magnesium, because sodium will be like going away from a noble gas, whereas magnesium will be going to become a noble gas. So that's the story with ionization energy. So to review, we've covered electronegativity, we've covered no, we didn't cover ionic radius. We covered atomic radius, and we covered ionization energy. So I do want to go back to radius for a second, because there is actually ionic radius. That wasn't a total slip up of me to say. There is ionic radius. So remember that an ion is a charged atom. So ion is a charged atom. What does charged mean? Well, it's going to have not an equal number of protons and electrons. And we don't gain or lose protons, at least not normally. So we're going to be gaining and losing electrons in order to get this imbalance. And in ionic radius, basically what you do is you compare the atomic radius of a thing that's neutral to the radius of the thing that's an ion. So, for example, if we look at our old friend sodium here, then what happens as we look at sodium versus sodium plus, so that's neutral sodium versus sodium that lost a negatively charged electron, then the difference between them when radius is concerned is we didn't change the protons, right? We did not change the attraction that the protons have on the electrons because the protons did not change. It's still sodium. If we change the protons, it would be a different element by definition. But we did change the electrons. We used to be in energy level number 3. Now we only have 2 energy levels. So we actually have less shielding in sodium plus than we did in sodium. So because of that, we are going to have sodium plus is going to be smaller and sodium is going to be bigger because it has more energy levels. If we look at another one, so for example, if we look at chloride or chlorine versus chloride minus, so here's chlorine in the periodic table, and if it loses, if it gains an electron, then it will become like a noble gas. It will get this electron configuration of argon. So we're going from neutral chlorine to chlorine minus, gaining a negatively charged electron, and what's going to happen is we didn't change the number of energy levels, right? But we did change the number of electrons, and we got one more electron. So the ionic radius of chlorine minus is going to be about the same as the ionic radius of chlorine, but a tiny bit bigger because we have one more electron and nothing happened to our protons. The other thing that they'll have you do with ionic radius, and the thing that's actually seen more often, I should have started with this, is they'll have you compare different atoms or different ions that have different protons, but they all have the same electrons. So for example, let's look at oxygen, fluorine, and sodium. If I have oxygen 2 minus, fluorine minus, and sodium plus, then for oxygen 2 minus, we gain 2 negatively charged electrons, we get to configuration of neon, which is here. If we gain 1 electron for fluorine, we get to configuration of neon, which is there. And if we lose 1 electron for sodium, because they're negatively charged, it is plus, but we're losing 1, we're going to also get to the electron configuration of neon. The other way to look at it is to count the electrons. So in oxygen, 8 protons, therefore 8 electrons, but then minus 2 actually means we gain 2 electrons because they're negative, so we get to 10. With fluorine, we had 9 electrons, but we're gaining 1 because it's minus and electrons are negative, we are going to get to 10. Sodium has 11 protons, so 11 electrons neutrally, but we're losing 1, so we get to 10. So they all have the same electrons. So the point is that they don't have any differences in shielding. What is different is their protons. So when they're isoelectric, or they have the same electrons like this, it's like they're all in the same row because their energy levels look the same, but the protons are different. So if you have more protons, but your electrons didn't change significantly, what happens to your radius? It goes down because you have more protons to attract the electrons in closer to the nucleus. So this would be the smallest, and this would be the biggest, even though these are in a higher row than that. So that's how ionic radius works. Most of the time they will give you a few elements and they will have the same electrons. I could not have given you this problem if I had said like O2 minus, F2 minus, Na2 minus. One, that doesn't make sense, but two, I'm not going to give that to you because then they have different protons and different electrons. And then you have two factors like fighting a battle in your head. So they tend to give you things where you have the same electrons for these ionic radius problems, and then you just look at the protons. But remember, for atomic radius, it was big here and small here. Let's do some practice. So let's focus on these elements here: nitrogen, phosphorus, and silicon. So looking at these guys, which one out of the three is going to have the biggest radius? Okay, so first we're talking about atomic radius, not ionic, right? Because I did not say anything about charge or plus or minus. So it's going to be big down here and little up here. Generally, it's going to go this way. So why is that? Because as we go down the group, we get more shielding. As we go across the row or period, we are going to get more protons to help attract everything closer into the nucleus. So with that in mind, silicon is going to be our biggest radius. Which one of these is going to have the biggest electronegativity? Remember that electronegativity is how badly do we want electrons. So looking at this trend as we go down the group, things get worse in electronegativity because you're going to have more shielding, which means more repulsion of electrons. But as you go across the period, things get better because we have more protons, so we have more attraction force. So looking at that, electronegativity goes this way, and nitrogen is the winner. What about which one of these would have the highest ionization energy? Ionization energy is going to be how much energy does it take away an electron. So in that case, what's going on is as we go down the group, ionization energy is going to get smaller because shielding helps us not care so much. Like we have so many electrons, we can just lose whatever we want, really. And as we go across the period, ionization energy is going to get higher. It's going to get more difficult to take away an electron because we have more protons to attract it with. So thinking about that, nitrogen is also going to have the highest ionization energy. So I hope this practice helped, and I hope that now you understand better periodic trends.